Hello everyone. In this video we're going to go through the Chapter 8 practice quiz. This is the first practice quiz. Right. So for our first question here, previous research has found that having a dog present reduces anxiety, stress, heart rate, cortisol levels, and pain. You wonder if human friends and therapy dogs are equally helpful while taking a stressful math test under a strict time limit. You randomly assign participants to take the test alone, with a friend in the room, or with a therapy dog in the room. After taking the test, participants complete a survey that assessed how stressful they found the test. Scores on the stress survey were measured on an interval scale, and higher numbers indicated greater stress. And the results of the omnibus F are as follows. So the first question asks you here about the interpretation of the p-value. So our p-value in this case is 0.002. Right, so this is a low p-value, and the data here are not consistent with the null hypothesis. Our null hypothesis would be that all three of those means are equivalent, that they're all estimating the same population parameter. And here this low p-value suggests they're not all three equivalent to each other. Okay. So in terms of which options here are correct, the first one that I just mentioned here is that the p of 0.002 shows us that the data are not consistent with the null hypothesis, right? So that is one possible outcome there. That's true. Right. Now, the other one that is a correct interpretation here refers to how it relates to the F. So first of all, remember that F's are all positive. Right? So all F ratios are positive. And what we're looking at here is the probability that you would get an F of 6.42 or higher if in fact the null hypothesis is true and that the treatment condition does not affect stress levels. Okay? So that is option B here. Okay. So let's talk, so B and G are the correct answers. Let's talk about why the others are not correct. First one, A, is not correct because we're looking at the probability of obtaining an F value of 4.2 or lower, and that is not true. F values are positive, and we're looking at F values of 6.42 or higher. The same thing is true for C here. We're looking at 6.42 or lower if the null is true, and there's no effect on stress. Okay. D and E both talk about the Post-Hoc test, and this p-value doesn't tell us what outcome we can expect from our Post-Hoc test. And then finally, F, the data are consistent with the null hypothesis is not true because you need a p higher to be consistent with the null. That would be a p more like 0.20. Okay. Next, we're looking at omega squared. So omega squared here is 0.08, and we're asking for the correct interpretation of omega squared. So omega squareds can be interpreted as the proportion or the percent of variability in the dependent variable that's explained by the independent variable. Okay. So in this case, our correct answer is the first one here. 8% of the variability in stress scores can be explained by whether people took the test alone with a friend or the therapy dog. Okay. So you get a percentage by moving the decimal over 2 places. Okay. B is not correct because it's looking at 0.08% of the variability, and that is 0.08 is the proportion. You should turn the 0.08 into a percentage by moving the decimal over 2 to get the 8%. Okay. Let's see. Okay. C is incorrect here. We say that there's a 0.08 probability that the variability in stress scores is caused by whether they took the test alone or not. The omega squared isn't referring to probabilities, and it's also not referring to causality. D, there's an 8% chance. Same thing, we're not talking about the chance that something is due to variability. It's the percent of variability, or the percent of the differences in scores explained by that independent variable. Okay. So all of these options here are talking about probabilities and chances, and none of these things are indicated by omega squared. Okay, for number 3, the results are in the tables below. So this particular output is a little bit hard to read because it's what you're looking at in Blackboard is a little bit clearer. But we have an alone group with a mean of 2.90, a friend group with a mean of 3.15, and a dog group with a mean of 2.30. Right? And then the numbers in parentheses are the standard deviations. Okay. The second table that you have looks at the actual post-hoc tests as well. So again, this format isn't great. Okay. All right, so I'm just going to pull over Blackboard real quick so we can see it in a better format. That we have alone, friend, and dog here in our table 1, and then the post-hoc test for table 2. Okay. So we're looking here, fill in the blanks for the correct interpretation of the effect size for the alone friend comparison. Okay. All right, so for the alone friend comparison, our effect size is 0.22. So that's a small effect. Right? So we have a small effect there. And then we want to know stress levels, were they higher or lower in the alone group than in the friend group? Well, if we look up at the table 1, we can see that stress levels were higher in the friend group than they were in the alone group. Okay, so you have to look at both table 2 and table 1 to answer that question. Okay. Next, choose the correct interpretation of the p-value for the alone friend comparison. So if I look at alone friend, the p-value is 0.31. Right? So 0.31, these data are consistent with the null hypothesis. Right? The 0.2 would be where we start to think the data are consistent with the null. And that means that the difference we're observing between the alone and the friend group is probably just due to sampling error. Next, we have number 5, fill in the blanks for the correct interpretation of the effect size for the dog alone comparison. So for the dog alone comparison, come back up here, dog alone, our p-value is 0.02, which suggests that this difference that we're observing between the alone and dog group is unlikely to be due to sampling error, and that it's a moderate effect. You have a 0.58, right? If we think about it's a medium-sized effect there for those. All right. So our data for the dog alone comparison, there's for number 6, we have moderately strong evidence against the null hypothesis. And it was a medium-sized effect that we're looking at. All right, going down to number 8, choose the correct interpretation for the dog-friend comparison. So if we go to look at the dog-friend comparison, we have a p-value of 0.001, has very strong evidence against the null, and the d is 0.8, which is a large d. And we can see the stress levels were higher in the friend comparison than the dog. So there were lower stress levels in the dog than the friend comparison. Okay, number 9. So the next question here, 9, which of the following is the best way to complete the write-up for this study? All right, so for number 9, I'll tell you right off the bat that the correct answer here is the last one. All right, so we're looking at the Fischer Post-Hoc test and showing that people who took the test with a therapy dog were less stressed than people who took the test alone or with a friend. Okay. The difference in the dog-friend comparison was large, while the difference in the dog-alone comparison was medium. Both of these differences were larger than what would be expected due to sampling error. People were somewhat more stressed when taking the test with a friend than taking alone, but this difference was small and within what would be expected due to sampling error, and so we're withholding judgment on this difference. And then we talk about there are no methodological flaws that are obvious, and the data are consistent with the existing literature. Right. Note that what's really important here is that we've talked about all 3 post-hoc tests. So it's really important to summarize what happened in all 3 tests and indicating both the size of the effect, the direction of the effect, and that is which group was higher than the other, and then also whether the difference we observed is likely to be due to sampling error. And so that's what's wrong with the other 3 examples. They vary in either they didn't talk about the size of the effect, they didn't talk about the direction of the effect, or they didn't talk about whether the differences were due to sampling error, or perhaps they also didn't even talk about all 3 of the post-hoc tests. Okay. Like for example, if you look at this first one, you know, it's going to take a really long time to walk through all these. I'm not going to walk through all of them. So let's just say the last one's the right one because it's done all of the things we suggested there. All right, next, suppose that you're concerned that the 95% confidence interval is too wide and you want a more precise estimate. What would give you a more precise estimate? Do the sample or do the study again with a larger sample size. Right? You're not changing the size of the population, but you're looking at increasing the size of the sample, which will decrease the standard error of the mean, which will make a smaller margin of error. All right, so now we have, starting with question 11, a set of data where you need to analyze the data yourself. So in this case, we have the data ready for you, so you're going to need to download it and pull it into Jamovi. Okay, so let me situate things here so you can see what we're working with. So I already have the data pulled into Jamovi for me, where I have group and stress score and their test scores here. Okay. So we're going to analyze the data, but first, before we do so, I'm going to change the wording or the labels for my groups, where 1 is alone, 2 is friend, and 3 is dog. So I'm going to click on group here and change 1 to alone, 2 to friend, and 3 to dog. Okay. And so that way my output will be labeled with alone, friend, and dog. Now to run the Anova, I'm going to click on Anova, and then Anova. Now my group is my fixed factor, and now our dependent measure is their test score. Stress score is what we looked at in the previous example. Now we're looking at their actual test scores. I'm going to ask for omega squared as a measure of my effect size there. Okay. So once I've done that, I get my Anova output summary table that I'm working with here. Oops, I'm going to make a little more room there. And you can see then that we have an F with 2 and 117 degrees of freedom. So 2 is first, 117 is second. The between treatment degrees of freedom come first, then the residual or within treatment degrees of freedom. And then the F that we computed was 3.98 with a p-value of 0.02. Our mean square error is the mean square residual, which is the 125.82. And then finally, our omega squared, need to move this over, our omega squared I'm seeing is 0.047, or in this case, it will be 0.05. Okay, so that's our APA style summary statement there. Our p-value is 0.02, which shows us that our null hypothesis is, the data are not consistent with the null hypothesis. The null hypothesis is that the test scores in all 3 groups are equivalent or estimating the same population parameter. And that's not likely to be true here. And so we're going to follow up with post-hoc tests. To do the post-hoc test, you're going to click on the post-hoc test menu and click on group and move it over. I'm selecting no correction. That'll give us the Fischer LSD test. And I'm going to ask for the Cohen's d with the confidence interval around it there as well. Okay. So to do this now, the question is asking the mean difference for the test score comparison between the dog and alone condition. Okay. So alone and dog, the mean difference is negative 4.975. Okay. So for question 12, we're looking at that difference there as negative. If you want to know which group is higher than the other group, you're going to need to look at the table of means. So to look at that, we're going to click on the estimated marginal means menu, move group over, and click on marginal means table. Okay. And that will give us a table of all of our means as well as a graph. Okay. So we can see that for this comparison, the dog and alone comparison, test scores were higher, better in the dog condition than in the alone condition. Okay. Now remember, when we're looking at stress levels, lower numbers are better, but test scores, higher numbers are better. Okay. All right, next we asked you to compute the Fischer LSD post-hoc test for the dog versus alone comparison. Okay. And we have a p-value for that test, dog alone And then follow that over to get a p of 0.04965, or 0.05 in this case. And then we're confishing, we want to know the standardized effect size for the dog alone comparison. Our D is negative 0.44, or sorry, it says negative 0.43 here, but it's negative 0.44. All right, now filling in the blanks for the correct interpretation of the effect size for the dog friend comparison. This is a different comparison that we're looking at. Okay, so in the dog friend comparison, we're asking test scores were higher or lower in the friend group than the dog group. So they were higher in the dog group than the friend group. Okay? And the difference in this case, when we're looking at the friend-dog comparison, is negative 0.61. So that's a medium to large effect that we're looking at there. So again, test scores were lower in the friend group than in the dog group, and this difference was medium to large in size. Next, you're going to choose the correct interpretation of the p-value for the dog-friend comparison. Our p-value is 0.007 for this one. So 0.007, that's very strong evidence against the null hypothesis. Next, you're filling in the blanks for the correct interpretation of the effect size for the alone friend comparison. All right, so for the alone friend comparison, test scores were higher in the alone condition than in the friend condition, right? But this difference was probably due to sampling error, right? And it's a small difference, right? So they were higher in the alone than in the friend, or another way of saying that is they were lower in the friend group than in the alone group, and that difference was small in size there, right? So your correct answer would be lower and small. 18, choose the correct interpretation of the p-value for the alone friend. Our p there is 0.456, and the data there are consistent with the null hypothesis. Okay, number 19, you are choosing the correct interpretation. So here I'm going to choose the correct one. I'll show you right here. It's this one that starts with overall participants who took the test with a therapy dog had higher scores than participants who took the test with a friend or alone. And so those differences were greater than what we would expected due to sampling error. Okay. So when we look at this, we're looking at the those with the therapy dog condition, comparing it to the friend and the alone. Right, so alone dog, we found that that difference was unlikely to be due to sampling error, and it was a medium-ish effect. And then also with the friend dog, it was also unlikely to be due to sampling error, and it was a moderate effect as well, medium to large. So I just called them both moderate here. Now, we also then have to talk about that difference that seemed to be due to sampling error. The differences in test scores between the participants who took the test alone versus with a friend was small and probably due to sampling error. So we note that there are no obvious methodological flaws in the study. We don't really have any information about the previous scientific literature, but we do note that the confidence intervals are pretty wide, and because of that, we'd want to replicate the study with a larger sample. And I can tell that the confidence intervals are wide. If we look at our output here, right, our confidence interval estimates for the 95% confidence intervals, for example, here are ranging between negative and small in one direction and moderately large in another direction. Right? So if you want more precise estimates, you need to have a larger sample size there. Okay. So the problems with the other options are all that either they don't talk about all three post-hocs, don't talk about P, D, and confidence intervals in their estimates, or something to that effect. Okay, number 20. This starts the different options looking at picking the right statistic. So in the previous examples, we tell you which statistic to use. It's a one-way Anova, so you know you're doing a one-way Anova in this chapter. Now we're asking you to determine which statistic is appropriate. Okay. So this one, for number 20, a researcher wants to know if thinking about death and uncertainty leads people to adhere to individualistic cultural values in the United States. So he takes 45 participants and randomly assigns them to either write about how they will feel at the moment of death, how they feel when they are uncertain, or how they feel when commuting to work. He then asked them to complete a questionnaire about the importance of rearing children to be independent. So that's a measure of individualism. And that measure of individualism is ranging from scores on the scale from 1 to 7, with higher scores indicating greater individualism. So in this case, we're going to be comparing scores on this individualism measure to these different groups, right? We have moment of death, how they feel when they're uncertain, or how they feel when commuting to work. There's 3 groups, and anytime we have 3 groups, it's a one-way ANOVA that we're working with. For question 21, we're looking here at, we have 50 people suffering from back pain, and they're randomly assigned to receive either 100 milligrams of a drug or 200 milligrams of a drug. 1 hour after taking their respective doses, they're asked to indicate their current level of pain, where 1 is no pain and 7 is severe pain. So we're going to compare the averages for those 2 groups. So we have 2 groups. They're independent of one another. There are different people in those 2 groups. And so because of that, we would do an independent samples T. For 22, a student wants to know how lonely students are at her college. To assess levels of loneliness, she asks a random sample of 430 students from her college of 4,000 students to complete the USCLA loneliness scale. Scores are measured on an interval ratio scale with a range of 1 to 5, with higher scores indicating greater levels of loneliness. She finds that the average loneliness score for her sample was 4.4. What statistics should she use to determine if her sample mean is higher than the population mean of 3.8? So here we have one sample mean that we're comparing to a population mean. So that means it has to be Z for a sample mean or a single T. We're going to choose the single sample T because we do not have a population standard deviation. You can always compute a standard deviation for a sample once you have the sample data, but you can't just get the population standard deviation unless you're given it. Okay? So in this case, again, our answer would be the single sample T. All right, for 23, a sample of 57 psychology majors were asked to indicate the degree to which they agreed with the following statement. It is possible to inadvertently create false memories during some psychological treatments. They responded by using a Likert scale where 1 equals strongly disagree and 7 equals strongly agree. Then the sample of psych majors watched a video on how false memories can be created. Finally, after watching the video, the psych majors answered the same question again. So did the video change their minds about creating false memories? So here we have the same group measured twice. We have 2 measures that we're going to compare. We're going to have a mean before the video and a mean after the video. Since these are the same people measured twice, that's a related samples T. 24, a student is planning to conduct a study on the effects of exercise on mood. She decides to use a survey to measure mood, and the survey has a mean of mu equal to 50 with a standard deviation of little sigma equal to 12. She plans to recruit 18 people who have not exercised in the past 6 months to participate in her study. All participants will exercise for 20 minutes 4 times a week for 1 month. At the end of the month, all participants will complete the mood measure. So here we have one sample mean. And so it has to be a Z for a sample mean or a single T. In this case, it's a it's a Z for a sample mean because we have the population standard deviation. 25, a statistics instructor wants to know if seniors, juniors, sophomores, and freshmen score equally well on his statistics exams. He uses records to find the stats exam scores for 50 students from each class year, and which statistics should he use to determine if one of the classes outperforms one of the others. So we're going to compute means for these 4 groups. And when we have 4 groups, we have to use an independent measures ANOVA. Finally, 26, a science teacher wants to estimate the amount of attitude change that would occur in a population of high school students if they watched a video on global warming. A higher score indicates a greater acceptance that human actions are at least partially responsible for long-term raising temperatures. She measured the attitudes of 36 students, shows them the video, and then measured their attitudes again. So we're looking at the means before and the mean after watching the video. So it's the same people measured twice, which makes it a related samples T. All right, and that is all for the one-way ANOVA chapter here.